Chapter 6, Section 4, the Rank-Nullity Theorem. The Rank-Nullity Theorem is a fundamental theorem that provides important information about the properties of matrices. This theorem shows the relationship between the rank of a matrix and the dimension of its null space. To understand the Rank-Nullity Theorem, we need to understand the concept of matrix rank, null space, and nullity. So, this section will start with explanation of matrix rank, null space, and nullity, and then we'll go on to the Rank-Nullity Theorem. We already know the concept of matrix rank, but let's confirm our intuitive understanding. The rank of a matrix represents the number of linearly independent column vectors in the matrix. Intuitively, the rank indicates the amount of information, or distinct directions, that the matrix contains. The higher the rank, the more the columns of the matrix point in different directions, and the more information it holds. Null space is the set of all vectors that are transformed to 0 by the matrix A. Specifically, it refers to the set of vectors x that satisfy Ax equals 0. Here, A is an m by n matrix. X is an n-dimensional vector. 0 is the zero vector, that is, a vector with all components equal to 0. The null space includes all the vectors that are transformed to 0 by the matrix A. For example, a vector x is in the null space if multiplying it by matrix A results in the zero vector. Consider the case of this matrix A and a vector x. For this matrix A, the vector x should be in the null space. Solving this system, we obtain a relation x1 equals minus 2x2. Thus, the vector that belongs to the null space is any vector of the form x1 equals minus 2x2. The nullity of the null space refers to the number of vectors that form the null space. In other words, the nullity of the null space is the degrees of freedom of the null space. This shows how freely the vectors in the null space can move. Specifically, it indicates how many free variables there are in the equation that defines the null space, demonstrating how much freedom exists for the solution. As an example, let's consider this matrix A. For this matrix, the dimension of the null space is 1. It means that the null space is formed by vectors that can be expressed with one free variable. Why is the nullity 1? Solving the equation Ax equals 0, we get the condition x1 equals minus 2x2, which means that the two-dimensional vector x has one component x1, determined by the other component x2. Thus, the number of free variables is only 1, and the null space forms a one-dimensional space. So, which vectors form the null space? In the example above, the vectors that form the null space can be expressed in this way. Here, x2 is an arbitrary scalar. Therefore, all vectors in the null space can be expressed as scalar multiples of the vector. As we saw in the previous slide, nullity is the degree of freedom of the null space. So, what is the degree of freedom? The degree of freedom refers to how many variables can be independently chosen or varied in the space. In this example above, the vectors in the null space are determined by x2, meaning the degree of freedom is 1. In other words, to determine the form of the vector, only one parameter can be freely chosen. Now, let's see what the Rank-Nullity Theorem states. For an m by n matrix A, the Rank-Nullity Theorem shows the relationship expressed by this equation. Here, A is an m by n matrix. Rank A is the dimension of the null space of matrix A. N is the number of columns of matrix A. Let's see an example. Consider the matrix B. To find the rank, perform row reduction. First, subtract 2 times the first row from the second row. Next, subtract 3 times the first row from the third row. The matrix in row echelon form shows one non-zero row, indicating that the rank of matrix B is 1. This means there is only one linearly independent column in B. Now, apply the Rank-Nullity Theorem. Since rank B equals 1, we have 1 plus nullity B equals 3. And thus, nullity B equals 3 minus 1 equals 2. The nullity of B is 2, indicating that the null space is two-dimensional. This means there are 2 free variables in the solution to the homogeneous equation Bx equals 0. In this section, we've explored the linear independence, which tells us whether vectors in a set provide unique directions or overlap. Linear independence is important to understand the structure of vector spaces and ensures that we work with the most efficient representation of data. We also discussed the Rank-Nullity Theorem, which bridges 2 important properties of matrix, rank and nullity. These properties highlight how matrices manage data and how much of it is unique or redundant. Thank you for watching. Please thumbs up and subscribe to my channel.